Thanks everybody for coming. I'm Steve, and it's not a bad turnout for a C# talk at a C++ conference, I think. So, I want to talk to you this afternoon about C# performance. This is me. If email and various socials you can find me on, it's probably not very difficult to discover me. But I'm going to start to think about the things that I've always been told don't. So don't work with children or animals. I don't think there's very much danger of that today, hopefully. Don't offer to present on C# performance at a C++ conferences. Sounds like a bad idea. We are going to talk about C# performance. Yes, I did intentionally pitch the talk and then almost immediately regretted it, but here we are. Hopefully you won't regret it as much as I did. And definitely don't attempt live coding, ever. There's only going to be a small amount of that because I'm not very practiced at it. So I'm ever so slightly out of my comfort zone. You may have noticed by the tremor in my voice. I'm fiddling with my rings. So why do I want to talk about performance in C#? Well, optimization is hard, famously. We'll get to that. And a few kind of misconceptions that we're going to cover. I've got a little roadmap that we'll talk about in a bit. But a little learning is a dangerous thing, famously. It comes from Alexander Pope. He went to say, little learning is a dangerous thing. Drink deep or taste not the Pierian spring. So we're not going to drink really, really deeply this afternoon, but we are going to take a look at some of the internals of C#, and we might even do a little bit of comparison with C++. That's going to be fun, isn't it? Also goes on to say about drinking largely instead of just a sip can be sobering. So looking more deeply, particularly when we're talking about optimization and performance, it can be sobering when you find out what's really wrong with your code. So we're going to talk a little bit about, just by example, some of the mistakes that programmers might make. And this applies not just to C#, it applies to all programming. We are going to try to talk a little bit more generally. Pope also had a couple of other quotable quotes, including the one about where angels fear to tread, which is quite often misquoted and taken out of context. I think that goes back to talking about C# performance at a C++ conference. So, but talking of misquotes, here's the famous one about optimization being the root of all evil. It's often taken out of context and left at optimization is the root of all evil. Premature is a word that's carrying quite a lot of weight in that. But also the bit where it says, or at least most of it. And optimization as an activity that you try to do as you go. So whilst initially coding something is mostly what Knuth is getting at, of trying to write optimally fast code first time. And that's the root of all evil part, because it very often results in very convoluted code that probably isn't necessarily faster than it would have been had it just been written as ordinary human readable code, let's say. So this is a quote that goes back to 1974. It's almost as long as I go back. So this isn't a new idea, and I'm sure everybody in the room has heard the quote before. So we are going to talk a bit about optimization, and I also want to compare it with the idea of pessimization, which is, that's a term I first heard from somebody at this conference, Jason McGuinness, about writing almost, well, it's very often unintentional, rather than intentionally writing suboptimal code. But there are practices which are well known to be bad for performance. And we're going to look at and one particular one of those in C#. But more generally, the same principles apply, I think. So some waypoints along the way, a few misconceptions, particularly about C# in comparison with other languages. A little bit of measuring performance in the wild. This is where the live coding comes in. I'm not going to do very much of the live coding thing, but we're going to look at some tools in the kind of .NET landscape and see where we can best make use of them to try and find out where bottlenecks in code occur. And we're going to look at what equality comparisons have to do with pool. This is pool in the sense of balls on a table played with sticks, like snooker or billiards. More pool or snooker, but we'll get to that a little later. So, in the beginning, or when things got interesting for C#, C# was designed not really as a C++ successor, but more like a Java successor, kind of. But that's a slightly political stance on that. But both Java and C# arose because C++ was considered to be very complicated, hard to learn. C++ templates had, they were really quite young, but already the idea behind, or some of the ideas behind template meta programming had arisen, so the whole Turing complete compile time computation. But C# wanted it also to be more sophisticated than Java, to provide, in particular, around type safety. So around about C#2, when generics were introduced, that's what I mean about when things get interesting. So C# took a very different approach to generics, to both C++ and Java, and tried to make things a little bit easier for programmers to grasp and learn, and hopefully remove some of the warts that were really quite obvious in C++ at the time. So whether they achieve that or not, that's a subject of a different talk, because C# for sure has its own collection of warts and problems and difficulties, especially since, as with all useful languages, it's grown and evolved over the years, and new features have been introduced, and sometimes those features play nicely with the existing stuff. Sometimes they don't. I'm sure that sounds familiar to everybody that's followed C++ standardization over the years. But there were criticisms, particularly from old C++ programmers, C programmers, that C# and Java, and most of these apply there, is that there are four main things that are obstacles to high-performance computing with a small HPC rather than what's commonly taken to be HPC. But garbage collection is the big one, where C# lives in a managed memory world with an automatic garbage collector that runs out of band to the program. And it's not necessarily predictable when it's going to happen. So this obviously goes against the grain of C++ being entirely deterministic in the operation of a program. You know what's going to happen and when it's going to happen, in a single-threaded world anyway. So the idea of some system-level thing hijacking your program in the middle of an important computation that's time-sensitive. So it's not an unreasonable criticism. Boxing is about how C# treats types. It makes a distinction in the language between value types and reference types. So reference types are, for the most part, the most widely used types, and that refers to the way that C# allocates things on a managed heap, which is what allows the garbage collector to operate. And they are the general purpose type in C#, but it has a specialized type called a value type, which doesn't live on the managed heap for the most part, for performance reasons. It's commonly held that they live on the stack, and that's sometimes true, but the point about value types isn't so much about where they live, it's the fact that they're not individually subject to garbage collection. So they live in the scope of another thing, whether it's a member of an object on the heap, or whether it's on the execution stack of a local function, or whatever it is. Boxing is when it occurs when you need a reference variable to refer to a value. So Java has this, I think, only for intrinsic numeric types, whereas C# has a more generalized concept of a value type. But if you need a reference variable for whatever reason, the common one being object, being kind of the ultimate root of the type system, object variables are always references. So if you take an object reference to a value, then it has to be boxed, which means it's copied to the heap. And the box becomes subject to garbage collection. And it's that copying. So value types are copied by value. That is their definition for C# programmers. There's a whole different discussion about what value type in a more general sense means. But in terms of C# as a language, value types have copy by value semantics. And references, whilst they have the reference itself is copied by value, the thing it referred to are very infrequently copied, and we'll talk a little bit about that. And then reflection. So we're going to mention reflection a little later because it's relevant, but C# has had reflection from the get-go, where you can introspect your code, reflect on it, in order to determine what the underlying or the intrinsic mechanisms of a compiled type are, but also be able to generate code or alter behavior. The point here is it's not really commonly associated with high performance for pretty good reason, but it doesn't usually need to be. So picking on the first one about garbage collection being it's unpredictable, takes a long time, interrupts program flow. These things, whilst true, have become less true over the years. So the garbage collection for C# or .NET programs more generally, it's the same mechanism, has been carefully optimized over the years to minimize all of these things. Unpredictability is much less of a problem than most people think it is. The fact that it occurs, but it can be controlled to an extent, because value types aren't subject to garbage collection. Again, this is something we'll cover. And that it takes a long time and interrupts program flow have become, the garbage collection has been optimized in ways that minimize both of those things. So garbage collection in C# has always been generational, by which I mean that when an object is initially allocated in memory, it's put in generation 1, and that's garbage collected much more frequently. If an object survives a garbage collection, i.e. there is still a reference to it somewhere, it is transferred to generation 2, and generation 2 is collected much less frequently. So the object stays alive longer, but you're optimizing the amount of time that you need in the garbage collector. So collecting generation 1 may happen relatively frequently, but it's fast because it's going to pick up all of the short-lived objects. Interrupting program flows become less of an issue with multi-pipeline, multi-CPU architectures because the garbage collector is multi-threaded. Unless you're absolutely saturating your CPU with your .NET program, then garbage collection isn't likely to interrupt your program flow anyway. And the deterministic destruction in C++ has its own cost. So if you've got, and this is a problem for any language, if you allocate huge numbers of very small objects in memory and you have to get rid of them somehow, in C++ you have to destruct them, even if a destructor does nothing. An optimized program may be able to optimize the call to the destructor away, but it might not. So it can still be an issue. It can still have a measurable cost. A similar thing applies in C# because if you allocate lots of short-lived objects on the managed heap, you're putting the garbage collector under undue pressure. And so you're provoking the problems associated with taking a long time and interrupting program flow. So we come back to this idea that value types aren't individually collected. The use of value types, quite a lot of C# programmers shy away from value types because the semantics are not commonly well understood by probably the majority of C# programmers I've ever met. And the fact that they're not individually garbage collected is a mechanism that you can use to reduce pressure on the garbage collector and make it more efficient. So we are going to talk about value types because value types are the most interesting thing about the C# type system. Reference types are just not interesting at all. Or rather, there are very many more use cases for them that it's impossible to cover every case. But in particular, we'll talk about how the garbage collector fits into that. So this is the recommendation in the Microsoft documentation. This is long-standing. So I've been working in C# since 2002 or 3, I think. So quite a long 2 decades worth of, and this recommendation has been in the documentation at least that long. So the idea of defining a struct, defining a struct in C# is what denotes it as a value type rather than a reference type. Define a struct if instances of the type are small and commonly short-lived. So by small, that varies, but small really is quite small. Commonly sort of 24 to 32 bytes. And the purpose behind that recommendation is about copying. So when you copy a value type, as I said before, it's copied by value, which means that you copy the variable, you get an entire copy of the entire contents of the type. So if a large type, if you're copying variables around, or copying the values of variables around, you're getting lots of probably, redundant copies of the data. And if it's big, it costs more in memory space and time to make the copy. So making them small reduces that. Commonly short-lived is, again, about the garbage collection. So if your objects are going in and out of scope a lot, just scope is a little bit of a measly word, but hopefully you understand what I mean. If very small objects are being created and immediately going out of scope or being copied into containers and the original's going out of scope, if they're being managed on the managed heap and subject to garbage collection, then that's undue pressure on the garbage collector. So making them value types reduces that pressure. And if they're commonly embedded in other objects, and that's another, that relates to both of these things, about short-lived and small size. Embedded in other objects can mean effectively 2 things: stored as a member of an array or other collection, or as a member variable. And what this really refers to is collections of stuff. So you've got large numbers of them. But as I said before, value types, they're not very well understood by quite a lot of .NET programmers. But being at a C++ conference, I thought I'd make that distinction instead. So thinking about C# string, which is a little bit more like the C++ string view than it is the standard string, because strings are immutable. The string is a reference type, so the contents of the string isn't copied frequently. And that relates to the immutability, because you can have 2 references to the same string object, and the fact that it's immutable means that copy by reference, so to speak, is benign, because you're never going to introduce a race condition or any other kind of side effect problem if you can't update the data by any of the references. The important thing in C# is that a C# string will never be boxed, because it's not a value type, because it lives on the managed heap. It is subject to garbage collection, which might be a problem for the short-lived objects recommendation. But a string is a value type semantically, because what we're interested in with string is when you compare two objects to see if they're equal, you don't usually care if it's actually two references to the same string. What you care about is whether the contents are the same, irrespective of whether you have two references to one string or references to independent strings with the same content. And it turns out that equality is quite important when we're talking about value types for multiple reasons, which I hope to explore. But before we do that, we need to talk about boxing. The GUID type is a built-in value type that's actually quite large. I can't remember how big, 96 bytes, I think. I can't remember off the top of my head. But this is an example of how boxing occurs. The example at the top, console.writeLine, again, it's another standard library type, if you like, takes a format string and then effectively a variadic array of objects. So the fact that ID is a GUID, which is a value type, means it will be boxed into the argument on the right. So you can avoid boxing in this case, because all WriteLine is going to do is call toString on it, which is a virtual method defined on the object-based class. So every instance of an object in C# has a toString. So if we call toString up front, we avoid the box. Part of the question is this a good or a bad thing to avoid the box? So arguably, this second example is a bit wordier, and it may avoid the box. Would anybody notice in terms of performance? Well, the answer is unlikely, because we're writing to the screen here, and the performance of that will swamp the cost of any box by many orders of magnitude. So the argument is that the first example, whilst it causes a box, and therefore it's only boxing one object, but it is introducing something on the managed heap that might not be necessary. But the code itself is slightly clearer, because you've not got the extra kind of mental noise of why am I calling toString? And if it's just to avoid a box, then it is just noise. So performance is a many-faceted thing. There is the idea of being optimally performant, but you might want to optimize for other things like code readability or testability or memory use. And okay, this would fall foul of memory use, because the top one would, because it's creating the extra copy on the managed heap, and therefore that becomes subject to garbage collection. But is it more readable? Well, I think it's a fine line, I know. Just an example. But there's more than just speed to consider. So back to string again. Started talking about equality being important. Strings are copied by reference because they're reference types. So when you copy a variable, as we do here, take a copy of original, all we're doing is creating a new reference to the same string literal here, a string. I would have made it a slightly better example, but I didn't have time, sorry. And the assertion is that this is an n-unit assertion. You may or may not be familiar with it. Hopefully, it's clear enough. What we're saying is we're asserting that the original is a reference to the same string as copy. They are two references to the same object in memory, and that passes. So strings are copied by reference, but they are compared by value. When you compare them for equality, or even less than, they are compared, it's the value that you're comparing, not the value of the reference. So here we're deliberately creating two references to strings with the same content, but they will end up with two separate references, because C# has a built-in optimization to do with the string table, where string literal, a string literal in a program is put into a table so that if it's used more than once in the program, you still only get one reference to it. So I'm hijacking that deliberately by creating a string builder and pulling out its contents. So here the assertion with asserting that it's not the same as. So we've got two independent references, two references to independent objects in memory, but they are equal because the comparison, the equals comparison, is comparing the content, not the reference. So C# allows, for this example, equals is a method that's defined on the object-based class, like toString. It's virtual, so you can override it. And the string class does. It overrides equals method to compare content. And that's important. This is what makes string a value-like type. In semantic context, strings are values. It's the content of the string that's important, not the location in memory or its identity. But there's more to equality comparisons than equals. Here's a simple type. It's a value type, as noted by struct keyword in the definition. It's read-only, so it's immutable. And it's just got 3 integer properties, which are init only. So init as a property accessor is a relatively new feature in C#, which means that you can write to it when you're creating a new object, and then once the object is actually fully initialized, those properties are read-only. And here it is in the code. The annotations, so I'm using JetBrains Rider. I'm not being paid by JetBrains to use their tools. It's just my preference. And we're going to use this type somewhere and make a hash set of these. I just want to go back to this. This is the default struct type. All we're doing is defining properties on it. The .NET provides a few other bits and pieces, and we're going to talk about that and why it's important. To demonstrate what's going on, here we've just got a little bit of link code, which I'm creating a sequence of 10,000 objects, effectively 10,000 pseudo-random numbers. And for each of the, so rng.next returns me an int, which is always 32-bit wide in .NET. And I'm using bit shifting and casting to byte to create one of those color objects. And then we're going to see this again. This is going to be a common pattern. The idea being I want to create a reasonably realistic collection of 10,000 probably different instances of color. So I'm using this seed. The reason I use 210 as the seed is just to make it obvious, because we're going to see that again as well. It's important because this is a pseudo-random number generator, and if I use the same seed in the same program for the same, if I run the program on the same version of .NET, it will generate me the same sequence each time I run it. And that's important because we're going to run the test multiple times. And I want it to be the same population of colors, but I want it to be reasonably randomly distributed. And then at the end of that, so I've got this sequence of colors and I'm using toHashSet, and that returns me a system hash set of type color for each of those 10,000 random numbers. And I'll just assert that it's not empty at the end just to make sure that it doesn't get optimized away. Any questions on that? Okay, good. So here's that test in a test. If I run it. that's passed. What I want to draw your attention to here is how long it took on the right-hand side. So that run took 15 milliseconds. That's not bad for 10,000 objects, right? I think that's pretty quick. So somebody comes along and says, well, because we're only using 256 possible colors for each of the red, green, and blue properties, it's going to be more efficient in memory if we make those bytes, because a byte is always 8 bits, only a quarter of the size of an int. So we're going to use less memory for each of those. It's not a completely unreasonable thing to do. So I'm going to rerun the same test. It's using the same type. I hope it is. Well, hold on a minute. That was 15 milliseconds a second ago. 577 milliseconds. I can run it again, and it will be approximately the same. 555. Okay, a couple of milliseconds off by running it again. Who knows? One thing I wanted to pull out from this is that recording the timings of your unit test turns out to be useful, a useful piece of information in your automated build, which you all have, right? Regardless of the language that you're using. Paying attention to these things can highlight potential problems, particularly if you graph them over time. And I'm sure you can imagine that if we used our previous color struct for a number of years and we had this little graph of testing times, and then we've just suddenly gone, and if you pay attention to that, that might be the indication of a problem. So, you can do this from a command line as well, just using the verbosity flags of .NET Test, but that's not the point here. So we made that difference to byte. What could possibly be using? I mean, we've effectively gone up 2 orders of magnitude. Pretty close to. What's going to be causing that? So let's go back to here. We can profile the unit test and have a look at sampling. What this is doing is taking periodic samples in the code. It effectively instruments the code as it runs to try and report information about how long different bits of the code took. And what we can see here is that it's create unique set, which is an internal method to creating a hash set, but it's taking all the time, and it's the toHash set is a particular problem within that. And we're going to look at this add if not present method in hash set in a bit more detail, because that's obviously where the cost of the problem is. But it's very, okay, equals is being a bit of a problem. So system value type equals, this is what a default struct in C# gets. All structs in C# have their own common base class between the struct itself and an object called value type. And that overrides, amongst other things, well, it overrides toString to do the same thing as the object base class, and the equals method. So because the equals method is called quite a lot when creating a hash set, it turns out, we're going to talk a bit about that in a bit more detail in a moment. So I can look at, where's my unit test? Right, let's look at the slides instead. Here's one I ran earlier. For the same thing, for those 10,000 structs, we look down at 2 hash set and we see equals is being 49, nearly 50 million times. And this is to create a hash set of 10,000 objects. That's a clue. So this is done with tracing profiling. So where sampling is telling you how long things took, tracing tells you what's actually taking the time. And it tells you the call counts for each of the methods. Said earlier I'm using the JetBrains tools for this. It's actually quite important because the Visual Studio profiler doesn't give you this level of detail for .NET programs. So the JetBrains .trace one is your friend. The other really good one is Redgate's profiler, which is, gives you similar level of detail and facilities as this. So why might we be calling equals 50 million times, give or take, for 10,000 objects? Well, if we revert our change to byte and turn them back to be int properties and rerun the tracing call, we can see that equals up on the top right-hand side is still being called nearly 200,000 times for 10,000 objects. So the problem isn't just about equals, and it's not really about byte fields, although it kind of is. The value type base class also overrides get hashcode. So for the worst case with byte fields that we saw where equals was being called 50 million times, the default behavior of get hashcode considers only the first non-null field in the type. So that's the red property. Why the distinction between with byte fields and with int fields? Well, when the fields are ints, there is some magic code in the .NET framework which uses a slightly different algorithm. It effectively does a bitwise comparison for the type as a whole. It's a memcomp, if you like, for the whole type. The reason it can do that for int fields and not byte fields is to do with padding. So it turns out that bytes don't really take up less memory than int fields or properties anyway, because they are put in their own word position with padding. You can control that to an extent, but it doesn't change the algorithm chosen at runtime to do get hashcode. So what that means is that we've now got, because it's only considering the first non-null field, the red property and the color type, we've got a maximum of 256 unique hash codes for our 10,000 objects, irrespective of how different they are. And the way that hash tables work, pretty universally, I think, is that they're a sparse array of buckets, and each bucket corresponds to a hash code. So if you've only got 256 unique hash codes, you're going to end up with buckets with lots of objects in. What does that mean? Well, let's take the worst case where we end up with only one hash code for our 10,000 objects. So we've got a hash, we begin with one element in our bucket. So it's going to be the same bucket because we've got one hash code, remember? So we've already got one element in and we want to put a new one in. So we perform one comparison to see if the element we want to add is already there, because hash tables are collections generally of unique objects. There are different types of hash table that exist, but the most common behavior is that hash tables are collections of unique objects. So we want to see if our new object is already in the hash table or not. So we make one comparison. We've already done the get hash code to determine the bucket. We found that it's a non-empty bucket, so we now have to call equals with the element in the bucket. So we perform one comparison. They're not the same, so it gets added. All good. Want to add another one. So we've already made one comparison. We now have to make two comparisons to see if we can add our new element in, giving us 3 comparisons in total. This one also is not already in the bucket, so we add it, and so on. The next time we want to add an element, we have to make another 3 comparisons, which is now 6 in total, and it gets added. And the result is that we've now made 10 comparisons to add 4 elements. And I'm sure you can see the pattern. This is what equals has got to do with pool. It's triangular numbers. So every time you add an element, you're making an increasing number of comparisons. The number of comparisons you need to make in that worst case is the triangle number of the number of elements, which simply is n squared plus n over 2. N squared. Hopefully that's ringing some sort of alarm bell for anybody that knows about performance and O notation. It's not as bad as it could possibly be, but it's not brilliant. So how does this relate to our 50 million calls to equals? Well, we had 10,000 color objects, which was causing very nearly 50 million calls to the equals method. So 10,000 squared plus 10,000, n squared plus n over 2 is 50 million. 5,000, that's suspiciously close, isn't it? That really is suspiciously close. It is because of, it all ties back to that default value type implementation of get hash code. Because it's not generating well-distributed hash codes, we're ending up with almost every time we add an element, we're probably hitting one bucket. I did look into that, and in the version of .NET that I was using, I had, I think it was 8 buckets that were populated in the collection for 10,000, and one of those buckets had the overwhelming majority. The other buckets had 2 or 3 objects in. So that explains the discrepancy between the actual 50 million, 5,000, and 49,960, whatever it was. So there was a little bit of distribution going on because there's this maximum of 256 possible unique hash codes, but we weren't getting that. And that's probably just to do with the way that the hash codes have been created by .NET. It does have an algorithm to generate hash code using prime numbers and bit shifting and some other complicated arithmetic, but it's not brilliant. It's not, in our case, it's not hard to generate unique hash codes for every unique object. Because we use bit shifting to pad them in from an int, we can use the reverse bit shifting to pad them out to an int. And this little algorithm will give us hash codes that obey the rules, firstly. So the rules are that 2 objects that are equal to each other by value have the same hash code, and that hash codes don't change. Those are basically the 2 rules. What this algorithm also gives us is that hash codes for objects that are different it's actually guaranteed to give you a different value, different hash code. Every unique color object will have its own hash code just because of the way that we were creating color objects in the first place. So, no prime numbers going on, no complicated arithmetic, just a little bit of bit shifting, and we've got what is an optimal hash code generator, okay, for our color object. I know life is not always that simple. Sorry about that. But for cases like this, it's really simple to create hash codes that are well distributed. .NET has a built-in, or modern versions of .NET have a built-in hashcode.combine, which also works and is efficient. In this case, it's not quite as efficient, but I've got other motives for not using it, which will become apparent. So we can override our own get hash code in color, to override the one that value type provides. If we do so, we should also override equals. And that's straightforward enough. What we're doing here is effectively using pattern matching to make sure that our object reference really is a color type. And then we are checking the properties in turn to see if they're equal. So that's a very simple implementation of equality. So let's up the ante a bit with our new implementation of color and create hash sets of 1 million items. So last time we were using 10,000 and we got horrible performance when changing the fields to bytes. Not going to do the change the field to byte, but it doesn't affect. Because of our new implementation of hash code and equals, it's not having the horrible effect that it was previously. What it does show when we create a hash set, so remember we're doing 1 million items now, so it's not going to be the same performance profile. But because we've effectively used a bigger lens, we've magnified the effect of everything, we can now see the effect of boxing going on. So every time equals is called, every time the equals method is called, the obj argument, or the argument to the obj parameter, will be a color, a value type. It's being cast to an object reference, which means it's going to be boxed. So copied to the heap and also subject to garbage collection. And we are seeing the effects of that. We're back to sampling. Oh no, it's still doing tracing. But we can see that the call we're making, what is that? 12,000 calls to unbox. That's probably not even all of them. There would have been a corresponding box for an unbox to map against. And okay, even though it's not showing up for all 1 million of our objects, it's still a measurable cost. So our next stage then is to implement the iEquitable interface, which is defined by .NET. And it's basically a type-safe version of the equals method. Where by type-safe, instead of taking an object parameter, it takes a color parameter. It's the type of the containing type. Key to that is that calling that method doesn't box the argument at all. We still have the override that takes an object, but .NET has magic in its collections to determine that if your held type is a value type and it overrides, or even if it's a reference type, you can override iEquitable, or you can implement iEquitable for reference types too. If there is an implementation of iEquitable, T, it will prefer the type-safe call to equals. So the one taking an object parameter ends up not being called. More modernly, we can use primary constructors to do a similar kind of thing, but there's no real significant difference here. Primary constructors are an annotation on the type taking parameters rather than an explicit constructor. And the names in the primary constructor are effectively in scope for the whole of the class definition, or struct definition in this case. So here we're just using those names to give initial values to those properties. The performance profile of both this and the previous one, where we used an ordinary classic constructor, are basically the same. Even more compactly, since .NET 5, we can use a sealed record. And since .NET 6, a record struct. So the difference here is that a record is a class that implements iEquitable and has other compiler smarts. A record struct, as its name suggests, is a struct. It's a true value type. So the first one is a reference type, lives on the heap, a bit like string, with overridden equals method and overridden get hash code method, and because the compiler is generating those methods rather than using a base class implementation, it can generate pretty optimal code for those. And it, in fact, generates almost what we saw for our custom implementation. It's pretty much the same as the equals method, and the get hashcode method uses hashcode combine. So, you know, they're comparable to each other, but it ends up with pretty succinct code. So we had a quick look at optimizations in the wild. Let's have a look at benchmarks. So benchmarks are slightly different. They give you more accurate timings than profiling. Profiling can give you an idea of where hotspots in the code are. So the sampling, profiling the sampling tells you which methods are taking the most time. And then profiling with tracing tells you which methods are being called most frequently. And those two things together can really help you pinpoint hotspots in your code. But if you really want to know how long things are going to take, then benchmarking is your friend. It's a much more accurate way of measuring programs, but it's much more difficult to measure just a unit test, as I was doing in the IDE of just right-click and click profiling. Benchmarks are a little bit more difficult. And as a result of that, the results are slightly less fine-grained. So whilst we can run profiling on individual unit tests and have different unit tests for different implementation characteristics, it's a little bit more difficult with benchmarking because you're benchmarking a program. It's most commonly. We're going to use a .NET benchmarking tool called benchmark.net, originally and imaginatively, but it's actually quite good, and it's pretty much the industry standard for .NET benchmarks. And here's what we're going to run. So first, we're not going to try the default struct where we've not overridden anything, because that would take too long. We are going to be doing this with a million items. So a simple struct with overridden virtual methods for equals and get hashcode. So that's the version of the struct with equals method taking an object parameter and then get hashcode doing what we demonstrated earlier. Compare that with a struct that implements equitable t, so that's a struct that has the type-safe version of equals. Some of the results are going to use the primary constructor, hoping not to see too much difference between those two things. We're also going to look at a class implementing equitable t, because I want to kind of pull out this idea about living on the managed heap versus not being subject to garbage collection, okay? And then we'll look at record and record struct as well and see how they compare to our custom implementations. So I'm not going to run this because it does take a little bit of time to run. This is for 10,000 objects. Oh, I thought it is only for 10,000. And it's the same. It's basically the same code that we've already seen in the unit test, but hoisted out with a main. In fact, I think I can show this. No, perhaps I can't. But just for memory, it's basically running this code again. So benchmark.net, you annotate a static class method with benchmark, and then you run the program, and it does a little warm-up to basically flush caches and pipelines and stuff, and then runs that method multiple times. In this case, it's probably run them a few thousand times and takes a mean, arithmetic mean of the results, and discards outliers and stuff, and does all sorts of funky statistical stuff to try to ensure that you're getting meaningful results. And what do we see here? We see that, so the top one, equitable color. So this is the class reference type that implements equitable. That's the worst performer, not by a huge amount, as we'd expect. The equitable color and the equitable primary constructor, they're within spitting distance of each other and significantly better. And that's directly because of the results of garbage collection and the overhead associated with that. The equitable color and equitable primary color are struct types, and so aren't subject to garbage collection. And the rest of the cost with the equitable color class is about garbage collection. So it is a measurable cost, even though it's not really a huge amount. The percentage difference is slightly, that's a little bit misleading. If we upped the element count to 1 million, we're not going to get a corresponding increase in the difference between equitable color and equitable color class. It will be collapsed because it's diminishing returns at that point. Interestingly, our type that only had the override taking an object parameter is the best performer. That's a bit of a shocker. I wasn't expecting that. That might just be an outlier, but repeated runs of this test actually show that the boxing is having much less of an effect than even I thought. It was a surprise to me that was the best performer here. And then record and record struct, they are comparable. So record is comparable to the equitable color, as you'd expect, and record struct is comparable, actually, a little bit better than our custom implementations. And again, that's repeatable. And this is because the underlying implementation of equals and get hash code for records and record structs. The .NET design, or the C# design team went to a lot of effort to make those as performant as they could be, whilst saving you having to write all the boilerplate for overriding equals and what have you. So, back to our common criticisms of C# about being predictable versus being fast. The managed runtime is helping us out here. Okay, we can use value types to reduce the amount of time that the GC needs to spend in clearing our stuff up. And then there is also the idea of just-in-time compilation versus ahead of time. It turns out the just-in-time compiler is pretty good at optimizing on the fly. And a lot of work has gone into making sure that it's not trying to re-optimize code that it's already done. Whereas ahead of time, it gives you better startup times for your programs, but there are far fewer optimizations available for it because it doesn't know what the runtime overall environment is going to look like, which the JIT compiler has access to that information. But here's fun. This is a color type, but this time it's in C++. So just remember, this is just for fun. Please. And I'm gonna try and construct a representative test that's comparable to the C# version. So here's our creating we're going to use unordered map rather than, because that's what hash set's called in C++, in standard C++. But here we're just creating a sequence as a vector, using the built-in random number distribution and using a little bit of ranges just because I needed to practice on C++ ranges. So views iota is a bit like enumerable.range. Views transform is a bit like enumerable.select. And then we're doing the same here where we're generating a random number and using transform to turn that the int. So we've got an int type. It's basically we're generating int, but the int type is specified as int32t here, just to make it, excuse me, because I didn't want, I'm running on a 64-bit platform, so my default int in C++ is 64 bits. In C#, it's always 32. The default int in C# is 32 bits, regardless of the platform you run on. So I wanted it to be comparable. So the int type is aliased to int32t. And we're using the same bit shifting algorithm to separate out the red, green, and blue properties of our color type. Wrong way. Here. And it's the same int type being used here. And we're overriding operator equals because there is no ultimate base class in C++. And that's a good and bad thing for reasons that are far beyond the confines of this talk. So operator equals is the first step that will allow us to put these things in an unordered map. It has to be defined. It's most efficiently, in this case, defined as a member operator. We can define it outside in C++, which is something we can't do in C#. But then we are risking the overhead of effectively inline method calls, which ought to be negligible, but I wanted it to be comparable because it's fun. So here we're just creating a vector of colors. We're not going to be measuring this, by the way. There's no point in measuring ranges. Tina Albrecht has already done this for you. She's got a great talk about throwing tools at C++ ranges, about their performance and memory characteristics and all sorts of stuff. I'll leave the link in there for you to investigate later. It's a great talk. But we are going to do, so I'm using Google Bench to do the benchmark test. So here we set up some global state with our create seeds method. So that's the thing that's create seeds method creates the vector of stuff. And what we also need in order to use an ordered map is a hash code generator. So here's our hash code generator, which is just because C++ defines these things differently. So the get hash code method is defined on the object-based class in C#. We don't have an object-based class in C++. We create a functor object for it. And we're doing exactly the same thing. All we're doing is calling into each of the properties and shifting the other way to the way that we constructed it. So we are going to be creating unique hash codes for every unique color object. Is this a fair comparison? Anybody think not? Well, that's good. So here's the benchmark. At the bottom is what actually does the thing. The setup is the thing that creates the global state and is not measured. And then the measured thing is the benchmark, and the unit, we want it to report in microsecond because that is basically the same order of magnitude recording as the other one. We're basically taking our global state, creating an unordered set from it. Sorry, it's run off the side. I ought to be able to scroll that. Yeah. So hopefully there's nothing unexpected about that. That's doing what everyday Joe programmer would do to create an unordered set from a sequence of what me, right? I'm Joe ordinary programmer. The reason for calling do not optimize is probably clear. The count variable's unused, so we don't really want the compiler to optimize it away, because if it optimizes the count variable away, it might realize it doesn't need the result at all and optimize that way as well, and that would be really pointless. It'd be really quick. It would certainly be a winner, which that code isn't. So here's our benchmark for the create benchmark. It's 681 microseconds, still with 10,000 of those color objects. Don't know whether you can remember. Here's the C# one. We're effectively, our comparison is really with one of these two, equitable color or equitable primary color, because we're talking about value types. So we're not trying to use pointers or any references in C++. It really is a value type. And we've written our own equals method. We've written our own get hash code method. So that's the comparison. We've got 135 microseconds here, and it's not even the fastest one. Okay. Nobody's actually jumping up and down. The unordered map is much faster than C# for lookups. But the point I'm trying to make here is that there is this headline idea that C++ is faster than C#, and I hear it all the time. And by and large, it probably is. But there are cases where it's not. And it's really important that you measure. these things. Because just taking kind of the common view might lead you to incorrect results. To be honest, this result really surprised me. This is using Visual Studio on Windows in a release build. And again, with the C# one, it's on Windows in a release build. Obviously, C++ compiler, C# compiler, the optimizations are going to be different. The underlying implementation of hash set and unordered map, unordered set are going to be different. And they have different optimization targets. So I didn't really look very deeply into why this might be the case, although I did do the relevant code to do lookups for each of the things. And that the C++ one outperforms C# by 2 to 3 times. So it's optimized for lookup. Whereas the C# one is, well, the optimizations lean more towards building the data structure in the first place. I did think it was interesting. We were also getting 1,000 iterations here. It's probably, I think the C# one was doing about 4,000 iterations. So Google Benchmark, if under the hood, is doing very similar things to the benchmark.net. It's doing the CPU warm-up, it's doing a test run to see how many it can do probably in a second, and then doing a run of 1 second each, and however many iterations that is, it turned out to be about 1,000. In order to give you a meaningful average result at the end. So the story really is measure. Don't assume that the code that you write first time is going to be optimally efficient. It probably won't be. It is possible to not, with a little bit of thought. I mentioned pessimization earlier, and our default struct that depended on the original C# implementation provided by the value type base class. I consider that a pessimization. It's not hard to override that behavior. And as we saw, the performance improvement that you get from that is huge for very little effort. And that it's my opinion that that doesn't come under the blanket of Knuth's original premature optimization. I think that that is avoiding pessimization to do that. Even more so than perhaps choosing to use the more modern features of record and record struct. Although there are other concerns that are at play in that decision as well. But the worst performance culprits are always the programmers. It's always the assumptions that you make in every case. And I proved it to myself with the C++ one. So again, that was just a bit of fun. But I'm happy to dig into that a little bit more. If anybody's really interested, we can get together over a pint. And I'll be interested to hear other people's opinions on that. People with more knowledge about it than I do. So here's a couple of handy links. Benchmark.net is just a NuGet package. You effectively build your code against it, and it's a library. But it hijacks the compilation step to ensure that you always get a release build, that it always has optimizations enabled, and then it reruns your code in a sane environment, if you like. Google Benchmark is just effectively a static lib for C++. Most easily, I used a CMake project. The Google Benchmark website has very comprehensive documentation, but very clear documentation on how to get set up if you're using CMake. And it just works, as long as you've got access to the internet from the machine you're doing it on. It is possible to do it in either kind of manually by downloading the header and a pre-built library. But CMake actually did make that a lot easier for me, and it did just work. Again, I was doing that in Visual Studio. I have done similar kind of thing with GCC, doing it in JetBrains C-Line, and it was similarly easy to do. So their documentation is really good, all available via that link. And again, anybody that's interested, I can go through the project. C# performance then. I wrote, the book's not really about C# performance, it's about value types. But I did do a chapter on which this talk is kind of broadly speaking based. I didn't, in the book, have the extra level of fun of comparing with C++. Thank you all for being kind about that. If you're interested, you can buy the book via these links or come and see me. I've got a couple of copies. I shall be at the wine reception later this afternoon. If anybody wants one, come and find me. And that's me done. Thank you very much. Any questions?
So you didn't show the benchmark.net code. I was assuming that you did the same thing in the C++ where you built an array of those colors first before then doing the 2-hash code in the actual benchmark.
I did, and you're right, I didn't show that code because I'd forgotten to preload it, and in the presentation mode of Rider, I don't get the Solution Explorer, and it's, yeah, happy to share that sort of afterwards, if you like. But yeah, basically doing the same thing. I'm deliberately not measuring the building up the original sequence with all the random number generation and the bit shifting. All I'm measuring is the 2-hash set in the C# one.
The parts where you showed that the colors you generated were mapped to basically the same bucket, the 10,000 colors by the C# runtime, that has to be a bug, no? Any hash function that maps like 10,000 unique values to basically one bucket, that just seems broken?
Where were we looking on this one?
Before you overrode the generate hash function in the C#. Yeah, but basically this, like that everything ends up in the same bucket.
Yeah, so it all comes down to this type, this default struct. The compiler doesn't give you any help here, but all structs inherit from value type, and value type has this default implementation of get hash code, which only considers the first field. The reason it does that is because it has to be applicable to any possible struct. And there is a similar problem with the implementation of equals, where for int type properties, as they are here, it's basically a memcomp to do equals. Changing it to byte forces the path through the value type implementation that uses reflection to go in and pull out each one in turn and do an object comparison. So you're getting boxing as well as reflection, as well as everything. It's as bad as it could possibly be. But the reason it's that way is when the structs have been with C# since the very beginning, and it was the only way that they could have the efficiency in the compiler, not trying to generate stuff, which they've, obviously, as the years have gone by, learned how to do better. But they had to create a base class that would be general enough to be able to work correctly, not necessarily optimally, for any possible struct. So I understand what you mean. Yeah, I mean, it would today be considered a horrible bug, but the constraints under which these operate is such that it's a reasonable, it's a reasonable implementation, and it is correct. It does the right thing, but not necessarily the optimal thing.
Hi, Steve.
Hi, Patrick.
Following on the results from C# benchmarking, the record color struct, you've got a table for that. That was pretty good.
It was pretty good.
And it also had I'll let you scroll through. Quite a large error. And I was trying to, is that, the size of that error, is that worth discussing, thinking about?
So, yeah, that's really just the confidence level. And it's a significant proportion. I don't know enough about statistics to pull that apart. Turns out that the level of error isn't repeatable across different runs. But I'd be happy to take advice from.
Right, we should probably run it again.
Yeah.
Like more. I've got another question, which is about, you just dashed off something about how the compiler-generated get hash code seems to inspect the struct and generate the optimal get hash code for a particular type. That's That seems kind of magical. How does it know to do that? Is it a reflection?
It's a compiler.
Okay.
So the compiler knows what your type looks like. In short, it's using system functions that do the magic to determine whether your type implements I-equitable interface. But the compiler generates in line all of the comparisons for the properties and fields that you've got defined. It's clever enough where I'm not going to go searching for the type. The properties that we've got are automatic properties, so the compiler has already generated hidden backing fields for those. And the same with record and record struct, where they end up being defined as automatic properties with backing fields, and the equals comparison is, or the compiler is clever enough to make the equals comparison use the backing fields rather than calling into the properties. But because when you define a record, okay, or a record struct, this is the same principal constructor syntax that I pulled out earlier, where it's parameters on the type itself rather than on parameters to a written constructor. And this provokes the compiler into, just from this definition, generating a constructor taking those parameters, 3 properties with the names, same names. They are, in this case, they'll be init only because it's a read-only record struct. An equals method, a get hashcode method, an equals override, a much funkier 2-string implementation, which does, basically, it shows you the packed contents of each of the fields in a nicely formatted way, and a couple of other bits which are used internally. But because it's the compiler, right? So it knows what the structure of the type is in terms of its fields, so it can then easily use that to generate the code to implement equals efficiently. By comparing the fields rather than using reflection at runtime, it's all done at compile time. Does that answer your question?
Got it.
I see. You mentioned that your attempt to save memory by turning ints into bytes doesn't really work that well because of alignment packing. If you had to deal with billions of these objects, what would you do to make it memory efficient as well as runtime efficient?
A different implementation altogether, probably. So if you were really that concerned about how much memory each instance was taking up, then C# has a number, there are kind of programmer level optimizations that where you can control the packing, you can control the padding, but you'd probably want much more fine-grained control over that with your own customized packed value for each one. And you'd probably want to be thinking about sharing representation as well. So there are tools that allow you that fine-grained control, but they're not really, if you really were working with billions of them, then you might care enough to dig into that. But for most applications, it probably isn't going to make enough of a difference.
Yeah, I was going to comment on like the hashcode thing being about again. Like I've seen like in C++ code being quite a reasonable optimization, which can lead into poor performance because of the same like binning problem with stuff like strings, where it actually truncates like the first n bytes and then forgets the rest of the string because it's faster to process those first n and then ignore the rest. So
Exactly.
It's a reasonable performance optimization, but as you saw, as you got down to a type where it's smaller, I'm guessing bool would be even a worse candidate.
Probably, yeah. So I didn't measure that, but yeah, that seems not unreasonable. The other thing about the hashcode combine, it kind of has the same constraints as the value type base class implementation. So it has to be general enough to generate reasonable hashcodes for a wide variety of types. Whereas we wrote our own because we had complete control over the type, and it's easy to see that just shifting the bits back out to an int is the same as shifting them in the first place. Hashcode combine and things like boost hashcode combine. The implementations are different, but the ideas behind them are similar, where the whole purpose of doing prime number or multiple prime number and lots of bit shifting and combining of values, that's done to try to address the fact that it has no idea of the type that it's working with. So it is a design constraint of those kinds of functions. But they are good enough in most cases, but it requires much bigger brains than I to determine why those algorithms are any good. But it's still not going to be as quick as the one we wrote for colour.
Hi. On your slide where you were looking at the larger case for benchmarking, for profiling, sorry, you were looking at 1 million cases.
Yeah.
You were worried that where you saw the unbox, you weren't getting as many as you expected, and you said you were worried that it hadn't counted them all. But surely you expect a small number there, because you're not actually hitting your equals method very often, because you've got a properly working hash code.
Partly. There's, I think that probably the more significant factor is going to be inlining. Because these are release builds, that's really bright. It's going to be inline. Was it this one that you meant about the calls to unbox?
Yes, that's the one.
So unbox it's a built-in system thing, but it is effectively a function. And the optimizer is free to inline it if it can, the same as any user-defined code. So I would probably expect that there will be, apart from the collapsed report that I'm displaying here, there will be further calls that might have 100 calls to unbox. And the unboxing is the more expensive operation between boxing and unboxing. Unboxing still causes a copy, but it also provokes some checks to make sure that your type that you're unboxing to matches and things like that. So it is slightly more expensive, but hopefully a later demonstration showed that actually the cost of boxing and unboxing is mostly not significant. Any more? Fantastic. Well, thank you very much for coming. I don't even know what time it is. Oh, that's not bad. Have 8 minutes back.